Today we're going to begin by talking about resistors, inductors, capacitors combined together in what is called RLC circuits. And we're going to begin with the natural response here. We're going to start with the parallel case. We'll get to the series case later, but you'll notice there's going to be similar patterns here as we go through this. So our goal here is to get an equation of state that describes the circuit, perhaps describes this voltage plus minus across all of the components, because you know since they're in parallel they're going to have the same voltage across them. We have some initial voltage on the capacitor here before t equals 0, and then at t equals 0 this switch is closed. You'll see how all of these things work together here. But keep in mind, this is probably not anything that we've seen so far in this course. Natural response, parallel RLC, and everything's got the same voltage across it. So let's do this. Let's sum up the currents. Let's say that's I sub C, that's I sub L, that's I sub R, and leaving that top essential node up there, you know that I sub C plus I sub L plus I sub R has to equal 0. Well, we know the relationship between voltage and current for all of these elements, so we can write that down. For I sub C, that's just going to be C dV dt. So we're starting with the I's, but we're going to write, this equation is going to be a voltage equation. Okay, plus, now the relationship between V and I for an inductor, you know that one, that is V equals L di dt, but we need to write this in terms of I, so we need to solve for I out of that. And you've seen this before. 1 over L, integral from 0 to sometime t later of V dt plus I at 0. Okay, that's the current through the inductor. And in our case, in our example here, there was no initial current, so that term would be 0. All right. Plus, now for the resistor, it's just V over R, and that's equal to 0. Okay, we've got an equation here. This would be our equation of state, but this is a difficult equation to solve. We need to do something to it first before we can hope to get a solution, because it's got first order derivative and an integral in it. So the common way to fix this is to take a derivative of it. In other words, differentiate it one more time with respect to time, and that eliminates the integral here. So let's do that. When we do that, we're going to get C d squared V dt squared for that term. And then here, taking the derivative of that, the constant goes away, and we're left with plus 1 over L V. And then when we take the derivative of this last term, 1 over R dV dt equals 0. Taking the derivative of 0, excuse me, just gives you 0. Okay, I'm going to rearrange the terms here. Divide through by the C, and I've got d squared V dt squared plus 1 over RC dV dt plus 1 over LC V equals 0. Ask yourself, does that equation look familiar to you? Is it anything that we have seen so far in this class? And if your answer is yes, then you don't know what you're talking about, because we've never seen this before in our class. This is a homogeneous second order ordinary differential equation. You cannot solve this by separation of variables and integrating through. So how do you solve this? Well, the correct answer, math person might disagree with me, but the correct answer is you guess at the solution. And the best guess is going to be something. We've got some function, that's the V here. Of course, there's coefficients in there, but ignore the coefficients for the moment and just look at the functions here. We got a second derivative, first derivative, the function itself. But when we add all of those three things together, it has to be 0. So you can almost estimate, well, what is a function that when you take the derivative of it and then take the second derivative of it, all of those will then sum up to be 0. Well, if you're thinking in terms of trigonometric functions like sines and cosines, you're on the right track. There is also another function that would do that, and that's the exponential. And yes, you have seen that one repeatedly in this class. So we're going to use the exponential, and we're going to assume that our solution has this general form, that v is equal to some coefficient times e to the st. Now that s is probably going to end up to be negative, but let's allow the negative sign to be absorbed inside the s, and let's allow the math to tell us whether or not that should be negative. Okay, let's test this and see if it's the right solution. We'll take the first and second derivative of it, and then plug it back into our equation here. When we do that, let's see, dv dt, that's just going to be a s e to the st, and then d squared v dt squared is going to be a s squared e to the st. Now let's take these and plug it back in. What am I going to end up with? We're going to have a s squared e to the st plus 1 over rc a s e to the st plus 1 over LC a e to the st, and that has to sum up to be 0. Now I can simplify this a little bit. Let's factor out the a, let's factor out the e to the st, that's common, and then we've got s squared plus 1 over rc s plus 1 over LC, and that has to equal to 0. Now, ask yourself, is our assumption here, our guess, is that correct? And the answer is yes, it is a solution as long as we can make this equation right here 0. And you ask yourself, well, a could be 0. Well, yeah, it could, and that would make this whole equation 0. But if a is 0, then why are we here in the first place? Because that means the voltage is always going to be 0 with that a there. What about the exponential? Well, if s is negative, it's a decaying exponential, so it would be 0 in the limit. Yes, true, but it's going to take infinite time for it to get to be zeros. Otherwise, it's not going to be 0. So while that is technically a mathematical solution, realistically, it's probably not a good solution. That leaves what's inside the parenthesis here. What's inside the parenthesis is a quadratic equation. And that can certainly be 0. And we can use the quadratic formula to try and find the solution for that. Now, I'm going to skip a few steps here. This s squared plus 1 over rcs plus 1 over lc, if you've taken a differential equations class, this is what is called the characteristic equation. And we're going to use a quadratic formula to derive solutions for this. And you know that we're going to have two solutions because it's a quadratic, so there's going to be an S1 and an S2. Now, like I said, I'm going to skip a few steps. I'm going to jump straight to the solution. You could use a quadratic formula and plug this in, and you would get the same answer. S1 is going to be minus 1 over 2RC plus the square root of 1 over 2RC squared minus 1 over LC. That's S1. And then S2, the only difference between these two is going to be the sign right before the radical minus the square root of that same stuff. Okay, those are our two solutions. So our equation back here, this one, has those two solutions I just showed you, and this is a solution to the second order differential equation as long as this is the case, that these are the solutions for S1 and S2. Either of those will satisfy that one equation, but we could write them this way. We could say, okay, well, voltage 1 is equal to A, and let's give this a new subscript because they don't have to be the same A now, e to the S1t, and then voltage 2 could be equal to A2 e to the S2t. They have different coefficients, so we'll give them different subscripts to indicate that for the different solutions. Now, from ordinary differential equations, there is this idea that if you have two solutions that work, then you can write a more general form of that solution as a linear combination. So a more general solution to our equation, to our second order differential equation, is just going to be the sum of these two things. If you'll think about that, let's say that the solution was all this and none of that, well then that coefficient would just be 0. If the solution were all V2 and none of V1, then the A1 coefficient would just be 0. So there is a way to manipulate these coefficients out front to show that the final answer is a linear combination of those two things. All right, now we're going to make some substitutions just to make this look a little bit more like, get it in the form that we want. We can say this, let's let alpha equal 1 over 2RC. So that's the term that's inside the parenthesis there. And then omega naught is equal to 1 over the square root of LC. Now, these two things have names. They pop up quite often. And if you look at the units for both of those are radians per second. So the radians per second, that should tell you that it's going to be a frequency. In fact, it's an angular frequency of radians per second. And so these are both called different types of frequencies. This one is the Nieper frequency, and this one is, this is the resonant frequency, the resonant radian frequency. We'll talk a little bit more about where that came from here in just a minute when I eliminate the resistor and show you what happens with that oscillation we talked about. But now let's just leave these definitions here and realize at this point that we can write S1 as a minus alpha plus the square root of alpha squared minus omega naught squared. And we can write S2 as minus alpha minus the square root of alpha squared minus omega naught squared, like that. Now these two are also frequencies. They also have units of radians per second, and these are called the complex frequencies. Now, the reason they're called complex frequencies, you can probably guess, is because what's underneath the radical could potentially be negative. If omega naught squared is greater than alpha squared, then this term right here is going to be larger. What's underneath the radical is going to be negative, and this is going to end up being a complex number. The alpha out front will be the real part, and the radical, what's underneath the radical, will factor out the imaginary number, and so you can see it's going to be a real part and an imaginary part to make these both complex numbers. Now, the complex frequencies are called that because of that complex nature of the S1 and S2. But you'll see this if we have a case where, let's say, alpha squared is greater than omega naught squared, then in that case, S1 and S2 are real numbers. So they are real and they're distinct. That means that they're different if alpha squared is greater than omega naught squared. So they're real and they're different. In that case, this is a special type of solution. That case is called the overdamped case. Now, the reason it's called the overdamped case is because if I were to graph what this looks like versus time, so if I were to take the S1 and S2, plug them back into our voltage solution here and graph the voltage versus time, then what it looks like is it may have some oscillation to it. It may start up high here and go down here, but it's going to take it a long time to reach t. In other words, it's going to reach 0 here in the limit. So that's called the overdamped case. Now, you could also have another case where alpha squared is less than omega naught squared. And in that case, S1 and S2, that's the complex case. In fact, S1 and S2 are going to be complex conjugates. How do you spell conjugates? Okay. They're going to be complex conjugates of one another. So you're going to have an alpha plus the imaginary part and alpha minus the imaginary part. So you can see they're going to be complex conjugates of each other. This case is called the underdamped. Damped in this case does not mean wet. Damped in this case has to do with friction, has to do with oscillation, has to do with how the oscillation behaves. For the underdamped case, the voltage versus time for that is going to look something like this. It's going to start up here and it's going to oscillate, 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 but the oscillations get smaller and smaller, and in the limit they reach zero as well. So that is the underdamped case. It continues to oscillate, but it eventually zeroes out. Okay, we've got one more case here, and that is the special case where alpha squared is equal to omega naught squared. And in that case, S1 and S2, they're going to be real. The solutions, S1 and S2 are going to be real values, but they're going to be equal. They're going to be equal to each other. And in this case, this is called the critically damped solution. This overdamped, underdamped, critically damped, if you've paid attention in your mechanics class, you may have encountered these before. Oh, by the way, critically damped, if I were to graph that, this is the solution where the voltage returns to the zero as quickly as it possibly can. You know, up here, it took a long time for these things to reach zero. But in this case, it's going to reach zero as quickly as it possibly can. Now, there may be some restrictions as to how quickly it can based upon your selection of R, L, and C values, but as quickly as the circuit allows it to, it will return to the zero value there. That's called the critically damped. And it could look like that. You know, it could look like that. It does different things, but it reaches zero as quickly as possible. These show up in what's called a simple harmonic oscillator. And that's what I want to show you right now. A simple harmonic oscillator is anything that has a period of oscillation to it. So one of the easiest things to talk about is going to be a mass. Let's say this is our mass M, and it's sliding across a nice flat floor. So this is a nice flat floor down here. And there's no friction on that floor. I'm trying to make it look level there. And attached to the wall here is a spring. And that spring is attached to the mass. Now, right here, that represents the zero position for the mass. But I could do this. I could reach here, I could grab the mass, and I could pull it out here, stretch the spring, and then let it go. Now, the spring is going to pull back. As I pull forward to the right, the spring is going to pull back to the left. But this spring is such that it also compresses, and when it compresses and goes past zero, then the spring is a little squished together, so the spring is going to be pushing backwards as the mass is going in that direction. So let's redraw that and talk about the force that may be on it. Let's say that represents the zero position, and I pull that mass way out here to some new position, let's just call it X, and the spring is stretched out. Well, as I pull it to the right, there's a force due to the spring that's going to pull it back in that direction. And that force is given by minus kx. And if you've encountered that sort of thing before, that force is known as Hooke's law. It's directly proportional to x. So in other words, as x is positive and going in that direction, the spring is in the opposite direction, and that's what the negative sign there. The K is called the spring constant, and that has to do with the characteristics of the spring itself. It's pretty much a set value depending upon what the spring's made out of, how many coils there are, how thick the spring is, and so forth. Okay, so that's known as Hooke's law. The same would be true if the mass were on the other side over here and the spring were compressed in that area. Even though X is now negative, there's going to be a force in that direction which is in the opposite direction of X. So that's why it's proportional to X, but it's in the opposite direction of whatever X is. So plug in negative X there and the F is in the positive direction to the right. Okay, if we write down the mechanics equation for this, F equals minus Kx, that's really the only force that is acting on that. After I pull it out and let it go, by pulling it out I am giving the system energy. But then when I let it go, there's only one force that's acting, and that is the force of the spring. We're assuming that there's no friction between the floor and the mass, so it should go forever. Well, that force has to be equal to mass times acceleration. All right, well, you may not recognize this, but this is a second order differential equation. Minus Kx is equal to mass times d squared x dt squared. So the acceleration is the second derivative of the displacement here. All right, well, we could rearrange the terms here. D squared x dt squared plus k over m x equals 0. Now ask yourself, what kind of solution would this have? And probably for this one, the easiest one is going to be some sort of trigonometric function. Something like x equals a cosine of some angle. And there's multiple ways to write this angle. We're going to write it as omega t plus phi. The omega has to do with how quickly it does its oscillation. And the phi has to do with at what point does it start its oscillation. So this is called the phase angle, and this is the angular frequency. So omega is angular frequency, and the phi here is a phase angle. All right, well, if you were to take this and plug it back into our equation here and test whether or not that is the solution, I will leave it up to you to do that. It is indeed a solution, but it's only a solution if that omega there is equal to the square root of k over m. So it is a solution. If we allow for this, then sure, that's the solution right there. But this is the case where there's no friction. Let's add friction now. Now, friction in this case, if you'll think about how friction is going to behave, friction is going to be related in some way to the velocity. In fact, if I were to redraw sort of a free body diagram here, there's x equals 0. Let's say there's maximum x right there. There's our mass. Here's the spring stretched out. Well, in this case, there's still the force F equals minus kx, and you can see that it's in the opposite direction of x, so they're proportional to each other. But there's this other frictional force, and this frictional force, let's call that little f, is going to be proportional to the velocity, but it's going to be in the opposite direction of the velocity. So in other words, if the mass is going to the left, the friction is going to be to the right. So we can show that a little bit more clearly, that friction is equal to minus some coefficient, we'll just call it b, times the velocity, which is dx dt, like that. And the negative sign is there just to indicate that this frictional force is in the opposite direction from the velocity. All right, so now the force that's acting upon the spring is going to be, well, it's going to be minus kx, but it's also going to be minus b dx dt, and that's equal to mass times acceleration, which is mass d squared x dt squared. Let's rearrange these terms now. Divide through by the m, and I've got d squared x dt squared plus b over m dx dt plus k over m x, and that's equal to 0. Now I want you to compare this to our equation that we just wrote down here, this equation here, and compare that to this equation here. You'll see that those have parallel forms. They have the same form. The coefficients are different. The variable x and v, those are different. But this is a second order homogeneous differential equation, just like that one up there. Okay, so what does that mean? That means that the solution for this one up here is going to look like the solution for this one down here. And they're going to have very similar characteristics, physical characteristics. So think about what this means. This may be a little easier to wrap your head around because there's some physicality to it. You don't have to imagine currents flowing through things. Well, let's see what's going to happen here. If there's just a little bit of friction, then the oscillation up here, well, let's start with the case of no friction. So if there's no friction, then what's going to happen is you're going to pull this back. This is x versus time. This is this solution here, and it's just going to be a continuous oscillation. It's never going to die down because there's no friction there. But if we add friction, there's really sort of three possibilities here. The first possibility may be the overdamped solution. In fact, why don't I just use this right here instead of redrawing graphs? Let's change this v to an x, to an x, to an x. With just, let's say the overdamped case, I'm going to say rather than just a little bit of friction, this has too much friction. So there's too much friction here between the surface and that mass. So what's going to happen is I'm going to pull it out here, and then I'm going to let go of it, and then it's going to drag itself back to zero. Maybe it never really gets back to zero, but it reaches zero in the limit. Okay, you see how that would work. Then what about the next case here? What about underdamped? Underdamped would represent this one right here, and it would represent a case where you only have a tiny bit of friction. So I pull the mass out to the right. There's only a tiny bit of friction here, enough to slow it down, but not enough to slow it down quickly. So within an oscillation or two, its amplitude doesn't change much, but it eventually dies down to zero. So it's going to oscillate back and forth, back and forth, back and forth, but the oscillations become smaller over time until ultimately it ends up back at the equilibrium point at zero. All right? And then this is, the next is the critically damped case, which is this one right here. And the critically damped is I pull it out, and what happens is it just goes straight back to zero. So it reaches zero as quickly as the system allows it to. It may go a little bit past and then return, depending upon characteristics of the spring and the mass. But it's going to go back to zero as quickly as it can, whereas these other two solutions, it's not going to go back to zero so quickly. Okay, so you can see maybe that gives it some physical significance here for our parallel RLC circuit, that we're going to have very, very similar situations. We're going to have not just one, two, we're going to have three potential solutions for our second order differential equation here. And I just wanted to show you that there are parallels between a real-life physical oscillating system and our parallel RLC. So that should indicate to you that our parallel RLC is going to have some oscillation to it. So there's these currents, these voltages, and this is the voltage equation here. The voltage is going to oscillate over time. Everything has the same voltage, but it's going to oscillate over time, and what form of that oscillation occurs depends upon which of the three cases we have. All right? Okay, one other thing, and then we'll get back to our RLC. There's an oscillation here. Now you might ask, where does that oscillation come from? Well, it comes about because of the fact that you've got the inductor and the capacitor in here. So let's just spend a minute talking about that. So you can maybe get an idea of where the oscillation comes from in the first place. There's the inductor, there's a capacitor. So let's say here that we have an initial voltage, some V naught, over here on the capacitor. So we've got an initial V sub C right here. And then I didn't put it in here, but we could put a switch in here, and that switch is closed at t equals 0. Okay, when that switch is closed, then you're going to have currents that begin to flow. And we could draw those currents in any direction. Let's say there's a current there, there's a current there, leaving this top node. This is I sub C, and this is I sub L. So just like before, I sub L plus I sub C is going to equal 0. Okay, well, I sub L, that's 1 over L V dt plus I at 0. And then I sub C, that's C dV dt, and that's equal to 0. Well, just like before then, I'm sorry, I left off the integral sign there. Just like before then, let's take the derivative of both sides. And when we do that, we end up with 1 over LV plus C d squared V dt squared. And that's equal to 0. Okay, I'm going to rearrange the terms here. I'm going to end up with a d squared V dt squared plus 1 over LCV equals 0. Okay, now have you seen anything like that before? The answer is yes, you have. You saw that just a second ago right here. Remember what case this was for, though. We have the mass on the spring, and this is with no friction. So there's no friction, and it oscillates forever, and the answer is just x equal a cosine omega t plus phi. So there's some continuous oscillation there. These three terms, the A controls the amplitude of the oscillation, the omega controls how quickly it oscillates, and then the phi controls the position on the graph, whether it's shifted to the left or shifted to the right. So you place the cosine on the coordinate system and give it an amplitude and a frequency based upon these three variables there, or those three coefficients, I should say. They're constant values. Okay, well, same sort of thing here. You're going to have a solution that says the voltage is going to be A times the cosine of omega t plus phi. It has to be that. It will be that. Okay, well then what does that mean? That means this is very similar to an oscillator, a simple harmonic oscillator like the mass on the spring with no friction. So without any resistance, assuming this is a perfect inductor, a perfect capacitor, perfect wires, there's no resistance whatsoever in this system. So what's going to happen? Well, it's going to oscillate forever. So think about this. The voltage that's on the capacitor here is going to cause a current to begin to flow. That current is going to pass through the inductor, slowly at first, but eventually it will go through until all of the energy from the capacitor is transferred into the magnetic field over here in the inductor. At that point, there's no more energy left in the capacitor. The energy is in the electric field of the capacitor between the plates. So the energy has effectively been transferred from the electric field into the magnetic field over here. But because the magnetic field no longer has a current to help maintain it, the magnetic field begins to decay. And at that point, the decaying magnetic field causes a current, which then builds up an electric field over here in the capacitor. So that'll take a little while, but eventually the energy will be transferred from the magnetic field into the electric field of the capacitor. And then the same sort of thing is going to happen again. You're going to have energy going from the capacitor to the inductor, back to the capacitor, back to the inductor, and back and forth and back and forth. There's no way that energy leaves the system unless you add in a resistor. So adding in a resistor is the equivalent of adding friction to the simple harmonic oscillator with the mass on the spring. So this thing would go on forever. This is an idealized case. It doesn't really exist, but it would go on forever if if we did not add the resistances. Now, in reality, everything has resistance. So even these wires will have resistance. The inductor itself, which is made out of wire, will have resistance. The capacitor will have some form of thing like resistance. So it's an idealized case, just like this is an idealized case. You never have a situation like this with no friction. So in reality, this is not real. You are going to have some resistance. That thing is eventually going to stop oscillating. And in reality, this thing is going to eventually stop oscillating as well. And that's the case where we've got an RLC circuit. So that brings us back to this right here. Okay, so we're going to have 3 cases for our RLC solution here. This is the equation of state. We've got the resistance added in here now with the L and the C here. The oscillator part of this circuit is the L and the C. The thing that dissipates away energy is going to be the resistor. And remember, it dissipates away energy at a rate of I squared R, like that. And so this is going to be very similar to the previous case with the mass over there. And you can see we've got our 3 solutions here. Okay, so now we're back to our RLC. Okay, well, how do you determine, if let's say you're given a problem, how do you determine which of these 3 cases you have? Well, you perform a calculation and you do a comparison between your alpha and your omega squared. Well, your alpha and your omega squared, you can see that they're related to the circuit components, to the resistor, the capacitor, the inductor, the capacitor here. So that is easy to calculate once you're given the problem. And then, based upon what those are, you know which one of these 3 cases you have. Now, there are going to be some things you need to figure out. For example, A1 and A2 can be figured out pretty easily, but you have to have information to do this. You have to have some initial conditions. You have to know what the initial velocity is. The initial voltage is. I'm looking at a V and I thought velocity. You have to know what the initial voltage is. You have to know maybe what the initial current is, and that will allow you to get to the voltage. Okay, so you're going to need some more information, or you're going to be given enough information so that you can figure it out. All right. So we know what the form of the basic solution looks like, and we've got 2 coefficients, okay? V equals A1e to the S1t plus A2e to the S2t. And if we knew, say, the voltage at 0, if you know the voltage at 0, then it's just this evaluated at t equals 0. And that's going to just be A1 plus A2. All right, so there's one equation that you can use then to help figure out what these coefficients are. All right, but there are actually 2 coefficients, so you need another equation. And one of the equations that's going to help with that is just going to be I equals C dV dt. Now this is specifically the I through the capacitor here. Everything has the same voltage, so there's no need for the subscript on the voltage. But if you know what the voltage is, if you know what the derivative is at t equals 0, or you know what this initial current is, so let's say that you know what I sub C at 0 is, then that's going to be equal to C times dV dt evaluated at t equals 0. Now, this is going to give you another way in order for you to get your second equation so that you can find that. Because if you take the derivative of this is going to be C, and you evaluate it at t equals 0, this is going to be C times S1A1 plus S2A2. Okay. Now, how did I get that? I took the derivative of this. I didn't show the steps, but I took the derivative of this and then evaluated it at t equals 0. The S1s come down here, the S2 comes down there, and this is what we're left with, like that. Okay? So this is one equation right here. The other side of that equation is this right here, so those are equal to each other. And then here is the other equation. So we've got two equations with two unknowns. The unknowns would be the A1 and the A2, and you can solve for those. Okay, so what does that mean? You need to know the initial voltage, you need to know the initial current through the capacitor, and with that you could solve this problem. Now, you may not be directly given the current through the capacitor, but you will be given enough information that you can figure it out. Given that little brief explanation, that really the problems are going to boil down to figuring out what A1 and A2 are for this type of solving this type of problem. You need to know that these three cases, the overdamped, the underdamped, and the critically damped, all three of those cases, the solutions look slightly different. No, they don't look slightly different. They look significantly different. And I'm going to show you, we're going to step through each of these three cases over the next video, and I'm going to show you how these three cases look differently. They all start with the basic solution. That's this right here. And then the form of that solution changes depending upon if we're going to have complex numbers for S1 and S2, okay? Or if we're going to have equal values for S1 and S2, or if they're real and distinct values for S1 and S2. So depending upon each of these three cases, this is going to look a little different. And we'll go through that next video.
But I can't sleep, so I don't dream. But if I could, I'd I hear a voice and so I freeze, but I can't move between the known and the unknown. I search for you, for you, for you.